So for FRAPPY number 3, we're given a table kind of like in FRAPPY number 2, but this one is a little different because instead of giving us the position of this rocket, it gave us velocity. So we can kind of think of this as giving us a table of the derivative instead of the original function. They also tell us that the initial height of this rocket A is 0 feet, so that might come into play later. So part A asks us for the average acceleration of the rocket from 0 to 80 seconds. So we've talked about average value of any function before, and it looks like an integral. So we can think about this as an integral, that we would have 1 over whatever our range is, so that 0 to 80, and then times the integral from 0 to 80. So this would accumulate all of the accelerations and then dividing by that time, just the same way that we normally think about an average, but we don't have acceleration. So we want to go ahead and talk about if we did find the integral here, the integral of acceleration is velocity, and then we would be plugging in our upper bound minus our lower bound. So we've got that v of b minus v of a over b minus a, and what do you know, it looks exactly like slope, because really the slope of velocity is going to be the average acceleration. So using this to evaluate, I'm just plugging in v of 80 minus v of 0 using our table here because they gave us velocity, and you should get about 0.55 feet per second squared. And we haven't gotten to talk about this a whole lot, but acceleration is talking about the rate of change. So we're talking about not just that it's going at 0.55 feet per second, but that it's actually increasing at a rate of 0.55 feet per second. Part B asks us for an interpretation of the integral from 10 to 70 of v of t in terms of the rocket's flight. So instead of taking the integral of acceleration, we're taking the integral of velocity. And if we remember back to particle motion, anytime we take the integral of velocity, we're either talking about displacement or total distance. In this case, it's kind of both because the rocket is still traveling upward, but just to be safe, because it doesn't have that absolute value, we can go ahead and say it represents the displacement in feet of the rocket from 10 seconds to 70 seconds. So it actually is the total distance, but it's the displacement from that 10 seconds to 70 seconds. And then part B also asks us to estimate this displacement from 10 to 70 using a midpoint Riemann sum with 3 subintervals of equal length. So that equal length part is important. We've had some tables where we just use whatever intervals they give us, but first of all, these intervals are uniform, so it is going to be easier to make them equal in length, but then it actually tells us that. So if we're breaking this up into 3 subintervals, and we're only going from 10 to 70, so I can kind of block off those other parts, I'm first just thinking through how I could split this to where it's even. And you could even take, from 10 to 70, it's gone 60 seconds. So we could divide that by 3 and see that it has to be intervals of 20 seconds. So that means my first interval is going from 10 to 30, from 30 to 50, and then 50 to 70. Now when I start to use my midpoint Riemann sum, they all are going to have a width of 20 seconds, but then the height is going to be the height that's in the middle of that interval. So for my first rectangle here, I'm going to have a width of 20, but then my height is going to be 22. I would have a width of 20 again, my height is 35, so just choosing that value in the middle, that's what that midpoint Riemann sum means, 20, and then my height of 44. So my midpoint Riemann sum should look something like this, where I'm using the velocity at 20, 40, and 60, and then actually plugging those in using the table. And remember, since I was taking that integral of velocity, this is telling me that it's traveled 2,020 feet. So then we get to part C, which is a little bit more involved. It gives us a new rocket, rocket B. It gives us an equation for the acceleration for rocket B. It tells us that at 0 seconds, the initial height is 0 feet for this new rocket, and then its initial velocity is 2 feet per second. The question we're trying to answer is which of the two rockets is traveling faster at time t equals 80 seconds. So for rocket A, we're just looking at the table to see that rocket A is traveling 49 feet per second based on our table of velocity. The part that's going to take a little bit of doing is trying to figure out what that velocity is for rocket B. Since we are given the acceleration for rocket B, that means if I take the integral of the acceleration, I will end up with the velocity. So looking at something like this, I went ahead and moved my t plus 1 to the 1/2. I moved it to the numerator so that it's to the negative 1/2. And then this is something that we need to use u substitution for. It's not a super complicated one, but we do want to go ahead and use u substitution. So if we make t plus 1 our u, then that makes du just 1 dt. So we can replace, we're not missing anything, we can replace that t plus 1 with u, and then our dt with du. I went ahead and moved the 3 to the outside so it can chill there. When I take the integral, I'm going to be raising that u to the negative 1/2 by 1 and then dividing by it. So raising it to the 1/2 and then dividing by 1/2. Cleaning up some things, so multiplying by the reciprocal with that 1/2 and then replacing my u again with the t plus 1 and then plus c. I kind of left it out there, but I do want to add that plus c, and that's where our initial velocity comes in, because they told us that the initial velocity was 2 feet per second. So that means that if my t is 0, my initial velocity is 2. So I'm going to go ahead and plug in both of those things and solve for my c. And we should get that c is a negative 4. Okay, so we're almost there. Now that we have our c, that tells us that the velocity function is that 6 radical t plus 1 minus 4. So I can plug in my 80 and find that the velocity at 80 seconds for rocket B is 50 feet per second, which, remember, for rocket A it was 49 feet per second. So that means that rocket B is traveling slightly faster, but we would say rocket B is traveling faster at t equals 80 seconds.